So in continuation of what I have discussed regarding the basic definition from unit 1, the first one is this definition of divisibility. Now I think I have discussed also a part of a part of this concurrence, definition on concurrence. So in general we can define it concurrence modulo m. Here you have m is a positive integer. M is a positive integer, which is a fixed, we can say that a fixed positive integer. A and B are any integers, they can be positive or negative, say. Then we say that A is concurrent to B modulo M if M divides A minus B. And we write A is concurrent to B mod M. In fact, in the other, we can say that A is concurrent to B mod M if and only if M divides A minus B. So there is a relation between concurrence and divisibility. Means we say that A concurrent for any A belong to set and M is a fixed positive integer. When you divide the difference of this A minus B, when you divide A minus B, or we can say that A minus B is divisible by M if and only if A is concurrent to B mod M. So how we define it? We say that A is concurrent to B mod M if and only if M divides A minus B. Or the other way also, if you have A is concurrent to B mod M, we can say that M divides the difference of A minus B. So remember this relation between concurrence and divisibility, that is A is concurrent to B mod M if and only if M divides A minus B. So here example, suppose you have A is an even integer and M is an positive integer, that is 2. Then plus or minus A, 0, plus or minus 2, plus or minus 4, plus or minus 6 are all residue of modulo M. And if A is odd, then plus or minus A, plus or minus 1, plus or minus 3, plus or minus 5, and so on, they are all residue of, they are all divisible. Means A is odd, then these are all the residues of, by residue we mean here B is called the residue of A, because A minus B is divisible by M. So note the remainder of A when divided by M equal to 2 is the smallest non-negative residue of A modulo 2, where 2 here it replace it by, where you replace M by 2. So these are the basic properties of concurrence. All this, the proof of this thing are in unit 1. Miss Marpa will discuss the in detail all this, even the proof also I think she will give. So what are the basic properties of concurrence? If A is concurrent to B mod M and C is concurrent to B mod M, then we say that plus or minus, we say that A plus or minus C is concurrent to B plus or minus D modulo M. So C2 here, if A is, so let me just say to you this one. Okay, if A is concurrent to B mod M, it implies that M divides A minus B. So this, or you can say that A minus B here is equal to M into K for some K belong to Z. Or you can write A is equal to B plus MK. Now C is concurrent to D, C concurrent to D mod M. It implies that C minus D is equal to M into R, where R is an integer. So this implies that C is equal to D plus MR. Or you can right now take this as equation 2 and this as equation 1. Subtract this 2 or add this 2, so you get A, the left hand side, from the left hand side of 1 and 2 you add or subtract. The right hand side also you add and subtract it from the right hand side. So you have plus or minus C. A plus or minus C is concurrent to B plus MK minus plus or minus D plus MR. So this can be written as B plus or minus D plus or minus, okay, M times of, you can write plus M times of K plus or minus R. So A plus or minus C is concurrent to this, or you can write here A plus or minus C is concurrent to B plus or minus D is equal. Okay, so, sorry, here it is equal first. Now if you want to convert this equal to concurrent, then modulo M. So we have the proof of this, that is, if A is concurrent to B mod M and C is concurrent to B mod M, then A plus or minus C is concurrent to B plus or minus D modulo M. The rest also the same thing using the definition. If A is concurrent to B mod M, then AC by multiplication, AC is concurrent to BC mod M. If A is concurrent to B mod M and C is greater than or equal to 1, then AC is always concurrent to BC mod M. If A is concurrent to B mod M and C is concurrent to D mod M, then AC will be concurrent to BD mod M. If A is concurrent to B mod M, then A to the power n is concurrent to B mod M for all n greater than or equal to 1. And if A is concurrent to 0 mod M, A is concurrent to 0 mod M if and only if M divides A. If you have AC is concurrent to BC mod M and GCD of C and M is equal to 1, it implies that A will be concurrent to B mod M. So all these things are needed. I mean, the application of this is needed in equation in unit 2. That's why I'm giving you all these basic properties of concurrence, though the proof I'm not going to give you. It will be discussed in unit 1 only. So if AC is concurrent to BC mod M and GCD of C and M is equal to N, then A will be concurrent to B mod M by N. And if A is concurrent to B mod M and N divides M, then A will be concurrent to B mod N. Since N divides M, so it will be concurrent to this one modulo N. For example, 17 is concurrent to 1 mod 8, since 17 minus 1 is equal to 16 and it is equal to 2 into 8 means it is divisible by 8. 21 is concurrent to 0 mod M, since 21 minus 0 is which is equal to 21, it is divisible by 7 and so on. Now if M does not divide A minus B, then we say that A is not concurrent to B modulo M. Because by definition of concurrences, A is concurrent to B mod M if M divides the difference of these two, that is A minus B. So here in this case, if M does not divide this, it means that A is not concurrent to B modulo M, and we write here A is not concurrent to B modulo M. For example, 17 is not concurrent to 1 mod 6. Why? Because 17 minus 1 gives you 16 and 16 is not divisible by 6. Similarly with the rest of the example. Now we come to the greatest common divisor. Note the number of divisor of any A belong to set A different from 0 is finite. The number of divisors of any A belong to set. Suppose if you have A is equal to 6 with A different from 0, as we have taken A equal to 6, then what are the divisors of 6? They are 1, 2, 3 and 6. So they are finite. So in general also, for any A belongs to set, the number of divisor of A is always finite. For if A is greater than 0 and D divides A, D greater than 0, then the divisor is always less than or equal to A. So the number of positive divisors of A is finite. If D divides A and D is less than 0 also, then minus D is a positive divisor of A. Hence the number of divisor of A is also finite. So the proof for this part. Thus, if A, B belong to set not both 0, then the number of common divisors of A and B will be finite. So let us define the definition of greatest common divisor. You have let A, B belong to set not both 0, then the largest of the common divisor of A and B is the greatest common divisor of A and B. For example, if you take A is equal to 6, B is equal to 3. So what are the common divisors of A here? They are, what are the divisors of A? 1, 2, 3 and 6. And what are the divisors of B equal to 3? They are 1 and 3. So what 1 is a common divisor, 3 is also a common divisor among these two integers. But what is the greatest among this? So 3 here is the common divisor of, or the greatest GCD of 6 and 3 is equal to 3. That is the greatest common divisor of A and B is called the GCD of A and B. So if you have GCD of A and B is equal to 1, say A and B, they are relatively prime, means we say that two integers are relatively prime if their greatest common divisor is equal to 1. For example, if you take a is equal to 3 and b is equal to 2, what are the common divisors of 3 and 2? 1 only. So therefore 2 and 3, they are relatively, okay, 2 and 3, not this d, therefore 2 and 3 are relatively prime. Basic properties, all these are needed in, all these basic properties of concurrence, divisibility and GCD are needed in the definition, in the proof of the linear concurrence, or how to find the solution of a linear concurrence of the next unit, or we can say that in unit 2. So here we have, let A, B belong to set not both 0, and let G be the greatest common divisor of A and B. Then what we have here is that G will be the smallest positive integer, means if G is a GCD of A and B, then G will be of the form AX plus BY, means you can always express G as a linear combination of A and B. Number 2 is, if D divides A and D divides B, then D always divides G. Okay, number 2 is this, if M is greater than 0, then the GCD of MA and MB will always equal to M times the greatest common divisor of A and B, and GCD of A by G, B by G, where G stands for the GCD of A and B, is always equal to 1. If you have here, GCD of AB is same as a GCD of B, and A is same as a GCD of A and minus B, and which is same as a GCD of A and B plus AX for any X belong to set. And if GCD of A and M is equal to GCD of B and M is equal to 1, then GCD of A, B and M will be equal to 1. And if A divides BC and the GCD of A and C is equal to 1, means that a GCD of A and B is equal to 1, it means that the GCD, then A will divide C only. Why? Because since the GCD of A and B is equal to 1, means the only common divisor between A and B is 1. So therefore it implies that A cannot divide B, which implies that A must divide C. So I think that's all from this unit basic definition of linear concurrence, GCD and concurrence, which are needed in unit 2. So if anything is not clear, because all this thing will be, Miss Marpa will do in detail all the proof of all these basic properties, right from the basic properties of divisibility and linear concurrences and GCD. So but I'll refer all this whenever I need the proof of this linear concurrence, how to find the solution of linear concurrence. I'll refer to this basic properties. So you have to read all those things. If anything is not clear, then you let me know. Okay. So that's all from unit 1. All those basic properties which are needed in unit 2.